welcome everyone to the Friday seminar. It's my great pleasure to introduce Chris Clarkson, who's visiting us this week. He did his PhD in Glasgow, then went for postdocs to Canada and South Africa, became a lecturer at Portsmouth University, and then went back to South Africa for a couple of years as a lecturer. Now he's a reader at Queen Mary, where we also collaborated. Maybe you know I've been there just before I came here. So he's one of the world experts in relativistic aspects of cosmology, and he's going to tell us today about the relativistic galaxy bispectrum. So take it away, Chris.
Right, thanks a lot. Thanks a lot, Julian, for the introduction and for inviting me over here and for the hospitality. Although a bit much hospitality last night, thank you. Yeah, I'd like to talk about some work I've been doing in collaboration with a number of people on the relativistic galaxy bispectrum, which, oh God. Okay, so this is some work with, God, right. So this is work with Steph Camara, Eileen de Weerd, who is a PhD student working on a lot of this stuff for the last few years. Shian Joliker, who's PhD student and postdoc at UWC in Cape Town. And Roy Martins, who's SK chair in Cape Town, and Bennett Rimmer, who's a postdoc in Portsmouth. So we've done a whole series of papers on this stuff, which I'd like to introduce to you today. So before I get into that, I thought, since I know a number of you are not cosmologists, I thought I'd just give a brief overview of the standard model of cosmology. So we have a fairly decent model of cosmology now, which started from some sort of big bang with quantum fluctuations seeding later structure formation. So quantum fluctuations are made classical through a period of inflation lasting tiny fraction of a second, blowing up quantum fluctuations to classical scales. The universe then went through radiation era, matter, and then a matter era, where the stars, first stars are born, galaxies are born, and so on. So that's a kind of the overall sort of picture. And a brief history of the universe is we've got the inflationary period, which seems to have actually happened, although it's kind of strange, where quantum fluctuations blow up to the size of the visible universe. The radiation era, which is where the first nuclei form, and the universe was a very, very smooth plasma state during this time. The end of that era is the cosmic microwave background, which I'll just go through in a moment. Then we move into the matter era, where galaxies form, and we're moving into a dark energy era now, where dark energy, seem to be observing, is taking over the expansion of the universe and accelerating it into the future. So the radiation era lasts about the first 300 to 400,000 years of the universe. During this time, we have a very smooth universe. The matter in the universe consists of plasma of radiation, dark matter, protons, and electrons. The protons, electrons, and radiation are all tightly coupled, so they move as one, and this plasma has oscillations in it, just like in the sun. So there's sound waves. But on top of the sound waves, we have gravity, and we have a horizon scale. And these three things couple together, producing a series of oscillations from the initial fluctuations, which we observe in the cosmic microwave background today. So we observe this in the same way that we observe a cloud. So in a cloud, photons are being scattered off all the water molecules in there before reaching the edge of the cloud and then free streaming to us today. In the early universe, at the end of the sort of radiation era, when protons and electrons combine as the temperature cools down below 3,000 degrees Celsius, the universe then becomes completely opaque for photons, completely clear to photons, and so they can then free stream to us today. And this provides an incredibly valuable piece of information, the cosmic microwave background. So shown here on the map is the Planck map of the whole sky projected onto this ellipse. And the fluctuations in there are a direct representation, a direct map of these quantum fluctuations seeded in the early universe, with some additional structure imprinted upon that from this oscillation period of the plasma in the early universe. So we analyze this by forming its power spectrum. So its power spectrum just takes angular scales, measures the temperature fluctuations on that scale, and we can plot this on this power spectrum on the left-hand side here. So on the bottom, we have an angular scale, so small scales on the right, large scales on the left, and we see a big peak in this with some higher order oscillations. And if you look at the actual map, you can see this peak by eye. There's a characteristic scale in this map of about 1 degree. Okay, so a degree the size of like one of these sort of red or blue blotches, or hot spots and cold spots in the cosmic microwave background. And those hot spots and cold spots around this scale are actually imprinted at late times. We can also observe these late times in the evolution of structure. So this is the state of the universe about 300,000 years after the Big Bang. Incredibly smooth radiation field. These fluctuations are about 10 to the minus 5. What happens after that is structure forms. The hotspots are overdense regions, the cold spots underdense, and so the overdense regions start to collapse into galaxy clusters. We can simulate these. Here's a box of a simulation. We can observe these. These are observations of galaxies. This is the 60F survey. So with us at the center, plots of positions of all the galaxies of where they're observed. And this zoom out of the background is roughly the current state of play of the observations of galaxies that are made up until now. So surveys such as 2DF and BOSS have scanned sections of the sky represented here in this diagram. And as we zoom out further, we can see further observations going backwards in time to this sphere of the cosmic microwave background all around us in every direction that we look. So that's kind of basic idea of the evolution of the universe. And today it might look something like this. This is a simulation of the dark matter today, of what it's a simulation of what it might look like. And if we just look at this simulation, we can see each dot representing a galaxy, roughly speaking. We can see that there's clusters of galaxies and areas with very few galaxies in between them. And this whole network of galaxies forms a cosmic web. And we can analyze this again with a power spectrum, which we'll spend a bit of time on shortly. But very roughly, the idea is that we have a power spectrum of structure. If we have the scale, here's a scale over millions of light years, and a characteristic density fluctuation for each scale is something where we have larger density fluctuations for smaller scales, going to smaller density fluctuations to very large scales where we measure them in the cosmic microwave background. The clustering pictures that we saw around these scales of 1,000 millions of light years, gigalight years across. So this power spectrum is an important tool for analyzing this map of the universe, if you like. So the idea is that we can take this complicated cosmic web and try and dilute it down into some functions that we can measure and then compare against simulations. And this is one of the key ones. So the power spectrum on the right-hand side and the 2-point correlation function on the left. So the idea of a 2-point correlation function is you take a map like I just showed you, and you take all pairs of galaxies and calculate the distance between them and form a histogram of distances. Okay, so a histogram of distances gives us this 2-point correlation function here, where with a small separation, there are lots of pairs of galaxies. And as we go to larger separation, there are fewer pairs at that separation. And this bump in it was first measured by the Sloan Digital Sky Survey, is known as a baryon acoustic oscillations, a direct visualization of the sound waves in the early plasma era. Now, the Fourier transform of this is the power spectrum, and it looks something like this. So we have large scales on the left, small scales on the right, and we characterize it with a wave number k, which is the inverse of the relevant wavelength. And it has a peak in it, and this tail here on small scales has been very well measured. On larger scales, it's less well measured, and around the peak is kind of an ideal area to measure it. So just to explain this with a bit more visualization, if we have our wave number here on the bottom, small scales on the right, very large scales on the left. So in a box like this, there are only a few modes bigger than these wavelengths here. At the peak is known as the equality scale. That comes from the period at the end of the radiation era when matter radiation was equal. So there's a big peak in structure, and that's a scale that you can see in this picture, sort of the distance between these large clusters roughly. Then there's some oscillations in here known as the baryon-acoustic oscillations. The Fourier transform of these oscillations is the bump in the two-point correlation function. So this is the power spectrum, which I'm going to spend a bit of time on. All right, so what do cosmologists want to know? Do these simulations, compare them with observations? What can we learn from that? Well, dark energy and dark matter are the key things that we need to know about, because they form 95% of the energy content of the universe. Dark matter, about 25%, is responsible for all the clustering that we saw in the previous picture. Those are actually dark matter simulations with no baryons at all, so no real galaxies in there. We want to know the details of structure formation. So from galaxy formation upwards, the details of that are very, very complicated. And how galaxies actually trace this dark matter, so where there's a clump of dark matter, how many galaxies do you expect near that, is known as a biasing. And that's a very complicated thing to understand theoretically. And so we'd like to know a bit more about that. Primordial non-Gaussianity is a thing that people talk about. This is to do with the very initial conditions in the early universe. So laid down at the end of inflation, what were the precise initial conditions? They seem to be almost exactly Gaussian, as measured in the cosmic microwave background, but there could be some non-Gaussianity to that. That is large wavelength modes where large wavelength modes on which all of the Gaussian fluctuations exist. And these can tell us about the exact nature of inflation, the nature of the inflaton itself. So this is something that large-scale structure can tell us, because over the scale of the box that we saw, the long wavelength modes of that tell us about the very early stages of inflation and any possible non-Gaussianity then there. And a further important question is, what's the theory of gravity once we get up to these very large scales? So is it general relativity? And if so, how do we know that's the case? How can we show that that's the case, given that there's this dark energy issue, which shows up at late times? In order to do this, there's a whole bunch of surveys that are being planned or in operation. There's the LSST, or the Vera-Rubin Observatory. It's going to measure many thousands of supernova points of light in the structure that we can then use to understand the distance to everything, to all the structure that we see. There's Euclid, probably heard a lot about. Here, this is going to trace the dark matter and dark energy by also measuring gravitational lensing of structure. So there's some uncertainty about when Euclid is going to fly, but hopefully in the next year or two. And then there's this square kilometer array, a giant radio telescope being built in South Africa, which will hopefully be able to measure in the radio all of this large scale structure. So we're going to be creating essentially a very detailed three-dimensional map of the universe. So the standard model of how we model that is essentially Newtonian gravity, just Newton's force law between pairs of dark matter particles. And those revolve forward in these two simulations that we can see here. These are both in co-moving boxes with the expansion rate of the universe factored out. So this is how the structure is modeled, Newtonian gravity, and all the stuff like galaxies painted on afterwards, light propagation is painted on afterwards. A question that some of us are interested in is this theory accurate enough? So by accurate enough is if we make sub-percent measurements of various cosmological parameters, will that actually mean what we think it means? Will there be bias from our models? So incorporating the full effects of general relativity is going to be important on these very large scales. So where non-Newtonian effects are coming into play. And in fact, as I'll argue, this will give us new probes of the universe by giving us access to these ultra-large scales. So let me just briefly go through an outline of what I'm going to go through. So I'm just going to review power spectrum in redshift space and discuss about how relativistic contributions come into play in this and give you a dipole in the power spectrum. Then I'll move on to the relativistic corrections in the bispectrum, which gets a little bit technical, so I apologize in advance. Okay. So the power spectrum that we saw before, where we plot against wave number the actual overdensity power, is measured in the sort of real space. So you take a simulation box, you imagine a constant time hypersurface, and then construct all of these various quantities, like the two-point correlation function and power spectrum. In reality, we observe on our past light cone. We don't observe spatial sections of the universe. We have a slice of it into the past. As you look out further, we're looking further into the past. So we actually see our past light cone. And that past light cone is distorted by various effects from general relativity and special relativity. So there's a fairly simple change to the redshift. So the redshift tells us the expansion rate out to whatever we're observing. So if we're observing in some direction n, looking at some overdensity over here, if all the objects are falling into that overdensity, when we observe in redshift space versus real space, a spherical distribution of galaxies that are all falling into the same cluster will become distorted in redshift space, squashed in this direction. So that's a basic idea behind redshift space distortions, and it's well understood. It gives a change to the power spectrum. So if we take a dark matter density field, delta of x, so in real space we have delta as a function of position. This represents the dark matter overdensity relative to the smooth mean. The galaxies trace this with some kind of bias. Okay, so it's kind of a sort of a fudge parameter b, stands for bias, and we reckon it's proportional to the dark matter density point by point. It's a very crude model. When we change this to redshift space from here to here, we pick up a factor where the velocities of the galaxies become important. Okay, so the velocity of the galaxy dotted along the line of sight, so the parallel velocity radially to and from us. We can't detect the angular one, but the radial one we can. Derivative along the line of sight gives us what's called a redshift space distortion. Now, if we transform this to Fourier space, so we take this expression, transform it to Fourier space, we have the dark matter density as a function of wave number k. So as we change the wavelength, the fluctuations in the dark matter density change as well. The galaxy overdensity as a function of wave number also change, and we now have this factor of the bias plus this extra redshift space distortion term. So F is here, there's the growth of structure, it just tells us how the velocities are related to the gravitational overdensity, an important parameter to try and measure. And the mu squared here is the dot product, or the angle between the wave number and the line of sight. Okay, so it seems a little bit arcane, but this is the factor responsible. The fact we've got a mu squared here tells us about the symmetry of this distortion in redshift space. Okay, as a twofold symmetry represented by the fact we've got a mu squared in here. Now, when we form the power spectrum is essentially the square of this field, and it gets rid of all of the directional dependence of k, except through this angle mu. So when we form the power spectrum of the galaxies, it's related to the power spectrum of dark matter, which has no directional dependence by assumption of homogeneity and isotropy. but the directional dependence in the galaxy distribution appears through this factor mu squared, which tells us about this squashing that we see in redshift space. Okay, so just to go through this in a bit more detail, got the angle between the line of sight and the wave vector leads us to what we call multipoles of the power spectrum. So the power spectrum has a dipole and an octopole. We can read through this mu squared term. Okay, so the way to do it properly is to convert to Legendre polynomials and then read off the multipoles from that. So the powers of mu determine what multipoles appear. Here, there's only even powers of mu, which lead us to even multipoles. And that reflects a symmetry that we see with this object in redshift space. If we rotate it by 180 degrees, it remains invariant. So it's symmetric about the line of sight, and there's no odd multipoles. This is a purely Newtonian description at the moment. So if we add in a relativistic contribution to this, how does it change? Well, we pick up an extra term which depends on the velocity. It's no longer the derivative of the velocity, just the velocity field itself. So this is the Kaiser redshift space distortion term, which will be familiar to some of you. This is the relativistic correction to it, where it just depends on the velocity along the line of sight. If we Fourier transform this, this extra term here, A is just a factor which I'll come to in a moment, just depends on the background expansion rate and so on. If we Fourier transform this, this gives us a factor of another factor of f, the growth factor. We've got a factor h over k, where h is the Hubble rate divided by the wave number. Now, the Hubble rate is important here because it sets the scale of the universe, basically, the Hubble scale. It's kind of some of the largest sort of scales that we're able to really measure in any detail. Excuse me. H divided by k means that this thing, if we're looking at wave numbers less than the Hubble scale, this number is less than 1. But once we're up to of order 10% of the Hubble scale, this will be of order 10%. Okay, so it means we can neglect terms for the most part that are this term squared. So we'll throw those away for most of this talk. Now, the important part about this thing here is the lack of an extra r derivative means that we've only got one power of mu in here of k dot n, which distinguishes it from this other classical redshift space distortion term. And so the basic idea is not that complicated, really. If we just take our redshift perturbation, calculate the observed position of a galaxy compared to its hypothetical background position, we do essentially a Taylor expansion. And then when we calculate the derivative of this thing with respect to position, we end up with this extra term with v dot n in there. So it's not a very complicated effect. At a basic level, a full calculation gives a few more terms when you have the whole general relativity machinery coming into it. There's a few subtle things that come into this factor A. One is the evolution bias and the magnification bias. So the evolution bias is the evolution of the co-moving density at a fixed flux cut for your survey. And the magnification bias is a change in the galaxy number density with respect to the luminosity cut at a fixed redshift. So these biases are survey dependent. They depend on the type of galaxies you're surveying and so on. They're quite sort of subtle things to model. And at this stage, it's worth just asking where the magnification bias comes from, because the magnification bias is really from a lensing effect, from gravitational lensing, making things bigger and brighter or smaller and fainter coming in and out of your survey. This comes into this galaxy over density because the lensing convergence term, kappa, is affected by this magnification bias, if you're interested in the details there. And lensing convergence actually has a Doppler correction when we look at it in redshift space. So stuff is bigger or smaller and brighter or dimmer, depending on the velocity of the object. And so this factor here, you can think of as a Doppler convergence or a Doppler lensing term, and we can make maps of it. So this is one that Julian did with our previous PhD student while in Queen Mary. These are the plots, maps of the Doppler magnification versus the weak lensing magnification at a low redshift of about 0.1. So on fairly large scales and shallow redshifts, this Doppler magnification correction is important and actually comes into this calculation of the overdensity thing. If we move to a redshift of 1, the Doppler magnification becomes a much weaker signal than the weak lensing magnification. So seen very clearly in these nice maps. So what happens to this term in the power spectrum? Well, when we square it to make the power spectrum, we calculate delta of k times delta minus k, or if you like, delta times delta star, the conjugate of delta. And when we do that, this term no longer has an imaginary part and just becomes purely real, which means that this term, which depends on h over k in the density fluctuation, now depends on h over k squared. So a 10% correction to your density fluctuation becomes just a 1% correction to your power spectrum, making it very, very difficult to detect in this form. So it's quite a small correction in this way. But now, if we take two different types of galaxies, which trace the dark matter differently, then the prefactors in all of these expressions will change. The bias changes, the magnification bias changes, evolution bias changes, which means if we calculate this cross power spectrum between galaxy type and galaxy type twiddle, we end up with this extra term in red here, which is both imaginary and scales as h over k. So it's now a much bigger signal in the cross power spectrum. And so in theory, then, this becomes a much larger signal that one could then hope to detect and then measure these various parameters associated with it. The imaginary part times mu corresponds to a dipole in the signature along the line of sight. So whereas the Newtonian power spectrum has a monopole, a quadrupole, and a hexadecapole, we now have odd moments to it, breaking the symmetry of the whole problem. So we now have a dipole where L equals 1 and an octopole, which is smaller still. So this then gives us a relativistic effect, which is less suppressed and is detectable via two tracers. So what does it look like? This is some work again with Julian, just showing what this power spectrum dipole looks like. It looks basically the same as the, if we look at this top left plot, it looks basically the same as the normal power spectrum with an overall amplitude shift. For those of you that followed this, this is corresponds more or less directly to the dipole in the 2-point correlation function that you get from the same analysis, but in real space rather than in Fourier space. We can also construct an observable for this in the angular power spectrum. I won't go into the details, but if you take an antisymmetric angular power spectrum, this is work Zeev Fonseca did, one can then isolate this Doppler contribution, and in fact, you can use this then to test the equivalence principle on very large scales. So this is an important aspect of testing gravity on large scales. Does dark matter, in fact, obey the equivalence principle? So by varying the relevant equation, we can then do a forecast to say how well we can constrain these two parameters associated with moving away from general relativity. So the cross is GR. Clearly, we can detect it very badly in one direction, but very well in the orthogonal direction. So this provides a new way to break degeneracies in this kind of measurement. Before I move on to the bispectrum, let me just mention primordial non-Gaussianity in this whole business. So primordial non-Gaussianity is something that supposedly we'll be able to measure in the power spectrum with next generation surveys. And the basic idea is the bias function now changes with a correction, which is proportional to the primordial non-Gaussianity parameter FNL. So this is just a number, maps onto various inflationary models. Inflation models predict a value for this number, roughly speaking. And the hope is that galaxy surveys can measure this thing down to about order 1, roughly. But now, if we notice the prefactor, we have a factor Hubble rate divided by k squared. Now, Hubble rate divided by k squared is the size of the relativistic corrections in the autopower spectrum. So if we just compare the autopower spectrum with an h over k squared, sticking this change to the bias in here, and we have another factor, h over k squared. And so the relativistic effects are then degenerate with primordial non-Gaussianity. So they need to be taken into account. Once we're approaching FNL of order 1, very challenging measurements, we'll need to add in these terms for that as well. And there's a whole host of other corrections that I haven't bothered going into in order to do that. So let me move now to the bispectrum. So what is the bispectrum? Well, the 2-point correlation function, where we take pairs of galaxies, measure the distance between them, do a histogram of that distribution. It's a 2-point correlation function. The Fourier transform of that is the power spectrum. And it's the main probe for growth of structure and this F parameter we mentioned, and for bias and things like that. Now we can form the same sort of statistic, but with triples of galaxies. So you take every triangle of galaxies that you can find and work out the distances between them, the shape that they make a plot of this. Then do the Fourier transform of this, and you form a fairly complicated statistic known as the bispectrum. And this tells us about higher order parts of the density field. It also tells us about non-Gaussianity. So for a purely Gaussian field, the bispectrum is 0. So where it's not 0 is through evolution of structure. It's a nonlinear process, so it breaks the Gaussianity of the initial conditions. But also, in theory, one can measure primordial non-Gaussianity through this statistic on large scales. And again, the hope is through measuring the bispectrum together with the power spectrum, one can get down to an FNL of order 1 and start constraining various inflationary models. But unfortunately, everything starts to get quite complicated. So let's form the bispectrum of a single galaxy survey. Turns out we don't need to worry about multi-tracer things for this whole effect. So we need this Doppler type correction up to second order, which we saw was just v dot n, velocity of your galaxy projected along the line of sight, with a prefactor which comes from the calculation. Now, at second order, we get a bit more of a messy thing. So second order in perturbative expansion, where we keep terms of order velocity squared. Instead of throwing these away, we now need to keep them. We need to keep potential times velocity terms, density times potential. So this is a leading effect at second order. And again, I've truncated this at order h over k. So you're neglecting millions of terms that come in at order h over k squared. Okay, so we have a big old mess of things. I'll just try and go through them. These coefficients depend on, again, evolution, magnification, and normal bias, as well as the derivatives of the bias and derivatives of the bias with respect to your luminosity cut and so on. So all the terms in this expression are projected along the line of sight. So they're all going to pick up mu's in Fourier space, factors of this angle. I'll just briefly go through them. You've got second order Doppler correction, Doppler times density, Doppler times RSD, gravitational potential times density gradient terms appear, Doppler times gravitational redshift gradient, and so on. And as well as things like the transverse velocity comes in as a correction as well in here. So this is a very simplified version of the full thing, which looks something like this. And this is again, not including quite a number of terms. This is calculation by kind of strange people like Daniele Batacca does this, Yarul does this sort of calculation. It's a bit scary. Oops. So anyway, we'll throw away all that stuff for now. So then we form the galaxy bispectrum. How do we do that? Well, we take, instead of 2 galaxies at different distances, we take 3 of them, Fourier transform that, it forms a bispectrum, and the bispectrum looks like power spectrum squared times these functions of the wave vectors k1, k2, and k3, which contain all of the physics of what's going on here. So these are known as kernels. We have, if we think back, we have the galaxy density fluctuation in Fourier space proportional to the dark matter density in Fourier space with an order 1 kernel, which was a bias plus f times mu squared plus a Doppler correction. Second order, we have an order 2 kernel, which comes in like this. So the details of the Fourier space thing isn't so important. But so we had the Newtonian one we saw already. There's a bias plus a growth factor plus this even power of mu. The second order Newtonian correction, this might be familiar to some of you, but if not, don't worry about the details. We have order 2 densities. We have a tidal bias, which tells us how the bias changes depending on the shape of an object in the tidal gravitational field. There's also a redshift space distortion term coming in at second order with a factor of mu squared in here as well. So again, an even power of mu pops into the Newtonian expression. How does the relativistic expression change this? Well, essentially, the full correction for the bispectrum breaks down into Newtonian plus a Doppler part or a relativistic part added onto that. Newtonian part we just saw is these kernels all multiplied together, all the permutations added in, all that sort of stuff. And the relativistic part comes in coupled to the Newtonian part. So it's a principle of long wavelength correction, but it comes in coupled to the Newtonian part, which of course applies on small scales as well. So here's some maths of it. The kernels I'll just briefly mention. So the first order kernel we saw before goes like h over k with a factor of I times mu. And that was what gave us the dipole in the power spectrum. The second order kernel is a bit of a mess. If you look at each of the terms, just scan them by eye, there's no need to go into the details particularly. Everything's truncated at order h over k. Every term involves a mu factor or a mu factor cubed. Okay, so again, it's odd powers of mu that come into here, which is going to break the symmetry in the bispectrum the way it did in the power spectrum. So the relativistic part then that comes in is now imaginary and goes roughly like the power spectrum squared times a factor h over k. And here's the full kernel if you're interested in expanding in powers of h over k. So beyond h over k corrections, one gets a lot of terms from metric perturbations and all sorts of other stuff. It becomes fairly unpleasant. Just a brief picture of what the bispectrum then looks like. The bispectrum depends on the shape of your triangle of Fourier modes. So your Fourier modes K1, K2, K3 must add up to a triangle. Depending on the shape of that triangle, gives you a different bispectrum. So it's much more complicated than just for the power spectrum, where just your length of your K vector matters. So here's a sort of plot of a couple of different bispectra for different triangle shapes, squeezed and equilateral, again at different redshifts. Here's a function of K, so small scales on the right, all the way out to the Hubble scale on the left. So this is like the largest detectable scale. Around here is the quality scale. And this upturn in here is all due to the post Newtonian corrections of higher powers of h over k. So what do we do with this expression? How do we go and analyze it? Well, much as we can with the power spectrum, we can analyze its multipoles. So we can just decompose it in spherical harmonics about the observer's line of sight. So if you've got your triangle of wave vectors, you can imagine decomposing that with respect to spherical harmonics around this line of sight vector from the observer. And then these coefficients BLM are just an invariant decomposition of the bispectrum. Now, the leading part of this is the dipole contribution. So if we form this multiple decomposition, just like for the power spectrum, the Newtonian part has a monopole, quadrupole, an octupole. No, sorry, a monopole, quadrupole, hexadecapole, all even multipoles, whereas the relativistic parts come in as odd multipoles, so they break again this symmetry. So this means that the bispectrum has a dipole moment, and it's due to the imaginary part, and it vanishes in the Newtonian case. So it's a direct signature of these relativistic contributions. It appears in the bispectrum for a single tracer of galaxies. You don't need the hassle of a multi-tracer survey to do this, to see this contribution. Oops. So I'll just go through a couple of different cases. So we did some estimates of what this looks like for different surveys. The galaxy survey is code for Euclid-like. Intensity mapping is a code for something like the SKA will try to measure. So B00 is the monopole. B10 is one of the dipole moments corresponding to m equals 0. B11 corresponds to m equals 1. The triangle shape is shown at the top. So here's a flattened case. Here's a squeezed case. And we can see, if we take the flattened case, at scales approaching the equality scale, it has a peak, and it's about 10% of the monopole. Similarly, for the squeezed case, we have around equality scale, so around here, we have a factor of 10% between the two. So the dipole is actually quite a bit larger than one might have naively expected. And again, we can do a similar sort of thing. So here, if we take instead of a triangle scale, we fix the scale and then vary the angle of the triangle, the shape of the triangle for a fixed size. We can see the shapes considered along the top here. So this flattened shape of triangle has a fairly big dipole signature of order about 10% of the monopole. Okay, so we have then a dipole which is kind of quite large, unique signature of relativity. There's actually a whole host of multipoles. Here's multipole L, so monopole, quadrupole. These are Newtonian contributions. We have a dipole contribution in here. So that's a schematic of the kind of multipoles that appear, and we can do nice plots. This is, Alina did this nice plot of the various multipoles. The amplitude is a function of triangle shape. So each point in here is a different shape of triangle. And we can see which multipoles with their electric and magnetic parts labeled here. Okay, so the dominant one is obviously the monopole. And then the dipole, we can see various different shapes in here producing a sizable dipole. Okay, I think. How much time do I have? Am I running out? Okay, so just to mention that the higher order contributions again mimic primordial non-Gaussianity in this. So when one considers the monopole to try and measure primordial non-Gaussianity, one needs to include these terms. Again, I'll skip the details, but if we just have an imagine of how the primordial non-Gaussianity and these relativistic effects intermingle, coming at order h over k squared, means for a given scale, they're degenerate with each other. And we can imagine an effective FNL at each particular scale that the relativistic effects produce, that if we mapped it into a primordial non-Gaussianity parameter, we would mismeasure. And so once we get to equality scales, so around here, we're looking at effective FNLs of order 5 or so. So this means if we're trying to measure primordial non-Gaussianity to below 5, we have to take these into account, otherwise we'll end up with a biased estimate. Let me just briefly finish then with a section on the detectability of these effects. It's very nice to work out the theory, or it's a great big pain to work out the theory, depending on what your perspective is. But do we need to? Well, in order to see this, we can look at the detectability. Can we observe the dipole in the bispectrum? So we're looking at a correction of order h over k times roughly the normal bispectrum. So we do the whole standard Fisher analysis, calculate signal to noise, analyze how big it is, and we do this for different surveys. So for different surveys, so if we take a Euclid type survey, we have a magnification evolution bias that looks something like this. These need to be calculated to figure out the signal to noise. Compute a signal to noise curve, and in each redshift bin, we've got a fairly weak signal of the dipole here. So a signal to noise of a few. If we calculate then the cumulative signal to noise, it actually becomes relatively sizable, which means that a Euclid-like survey, if it ever launches, should be able to detect this kind of effect. So what modes are important to this? Do we necessarily need these long wavelength modes in order to make a good detection? It turns out the sensitivity to your volume of your survey is not actually that strong, which is a little bit surprising. So if we change the longest mode in the survey by an order of magnitude, it drops the signal to noise by a factor of 2. So the long wavelength mode actually isn't that important, even though it's a long wavelength correction. Excuse me. Are the second order effects important? Is this massive calculation worth doing? Well, it looks like if we calculate the signal to noise in the dotted curve without them, we end up with just half the signal. So half the signal seems to come from these second order effects. Okay, so we did the same for intensity mapping, can just about observe it there. So let me just finish with the conclusions. So the galaxy bispectrum then has large-scale relativistic effects, which appear at order h over k compared to h over k squared in the autopower spectrum for a single tracer. So we've got, there's a local effect from Doppler and gravitational redshift, and the coupling between the two. There are also integrated effects which come in, which we haven't analyzed yet. So we have a dipole in this, which is a unique signature of relativity. It doesn't appear in the Newtonian analysis, and it should be detectable in the next generation of surveys. Okay, so I'll leave it there. Thanks for your time.
Okay, thank you very much. Do you have questions? We do.
Yeah, very nice talk.
Thank you.
Maybe if you can say a few words about these cross correlations that you mentioned in the beginning for the bispectrum. So what would be an ideal, what would be ideal tracer to maximize that signal?
Oh, so for the multiple tracer,
exactly,
for the multi-tracer power spectrum. Oh no, I can't remember what the actual optimal thing is. There's a number of papers I can point you to.
So is it, does it depend on the difference of the bias between
yes,
the two?
Yeah, that's right. So that's one thing to optimize is the difference between the two, since it's proportional to B1 minus B2. And you can also look at cross correlations between galaxy surveys, intensity mapping, and things like this. So there's a large series of papers by Roy Martins, Steph Camara, Say Fonseca that have looked into this in quite a lot of detail.
Okay, and so if you would get, for example, a tracer that has a negative bias, that would be ideal, or?
Well, it would help, I would think. Yeah.
Okay.
But also the evolution of magnification bias seem to be quite important as well.
Like a point. Well, for example, if I don't know if that works in that, but for example, if you have reionization, essentially zero around galaxies, because it's ionized signal, and the signal comes from the voids, but then you don't have a lot of galaxies there. So.
Oh, that's interesting. Right. Okay, that's an interesting idea.
So this is maybe a very simple question, but very interesting stuff. But how does this link like the very big questions cosmology posed in the beginning? So
yes. So okay, so that's a really good question. So it provides new ways to test general relativity. So accessing these large scales gives us ways to test the equivalence principle on large scales that you can't do in perhaps other ways. In a sort of more like negative sense, if we're trying to measure primordial non-Gaussianity to learn about inflation, basically this is just we have to include this in order to get the correct answer. So it's a bit less than exciting, more work to do sort of thing. Yeah, so those are the two main effects. And of course, if we're trying to measure the growth of structure and bias and things, this is a sort of extra thing that needs to be added in, I think.
I didn't get follow all the details now. So in all the charts that you include right now, are you still at the distant observer limit? Or?
This is all a distant observer approximation, and wide angle corrections will come into this at a similar order of magnitude. Yeah, so that's an ongoing calculation, which is much worse than I thought it would be. It will need to be included, yeah. So this is like an idealized case at the moment. Yeah.
I just had a basic question that maybe you did it in your introduction, but I wasn't sure. And that is, you're looking at large scales for these effects. And naturally, one would think that the CMB has very large scales.
Yeah.
Why is that not the probe that you focus on, where you don't have to worry so much about bias?
Yeah. So the CMB includes all the relevant relativistic effects that's required. So the CMB is kind of like done, if you like, and this is sort of late time structure formation of the equivalent kind of relativistic contributions that come in. So I don't know a huge amount about the CMB in detail, but you wouldn't need situations where a patch of the CMB is moving towards or away from you is automatically included in that analysis to all relevant accuracy.
Okay, but the precision of CMB measurements is very high. Just wondering why one would have to go to Galaxy. What's the motivation to go to galaxies?
Well, yeah. So one is that we're going to be measuring these things anyway. The other is that galaxies trace a nonlinear distribution of matter, whereas a CMB is completely linear, to all intents and purposes anyway. Whereas by the time you're looking at 10 billion years of evolution, there's an awful lot gone on in that period that tells you about the theory of what gravity is doing over that time period, for example. So the growth of structure, this F parameter, the growth rate, will depend on things like your theory of gravity, for example, and that all comes into these things.
Yeah, so I think in the CMB they have constraints on FNL.
Yeah, that's right.
Just remind us what they are.
So they I think, I'm not sure exactly, but it's of order tens. I think it's been measured. Yeah, 50 or so, and I don't think it's going to get much better anytime soon from CMB. So people argue that large scale structure will get down to order 1. I think that's probably unlikely in the next few years, but achievable. As T tends to infinity, we'll get to that level from galaxy surveys. So that's kind of the motivation for this. Yeah.
Can I just add something there? So I think another generic argument, which is like LSLs is going to be better than CMB, just the fact that 3D information, right? So you have one more power of number of modes, and especially at large scales with your pouring modes, it's also important, right? CMB, you're just looking at 2Ds. So you have the lenses, you do learn something also about but it's essentially 2D information, right? So in terms of how much information content, LSS I guess this is how you get these expectations about FNL and all too. I mean, it's completely different sensitivities too, but it's also the sheer number of modes.
That's a good point. Yeah.
I just hear it around a lot. So qualitatively, it's something that is quantitatively, I don't know exactly, but how much
I think
cube instead of square, right?
I think the devil will be in the details. So. Some models.
Well,
no, so like so not single field, but I think multi-field inflation gives you generically larger FNL. But I think from what I know of inflation, which isn't a great deal, the class of models with FNL larger than 1 is actually quite a small subset. And typical inflation models have about FNL of order 10 to the minus 2. So there's actually quite a long way to go in order to get to that.
And actually arguably also 0 non-detectable.
Yeah, maybe. But you never know.
You can just remove it with a single coordinate. But yeah.
Yeah.
We have
A very short one. So you said that so what about the surveys that are actually ongoing, like DESI?
So that's a good question. I think DESI is I think it's on the edge of being able to measure this stuff. So Cami Bonvin's done some forecasting for DESI, I think, and its ballpark should be detectable. So it just needs somebody to start doing it, I think.
We're looking at it for the dipole of
Is Euclid gonna be better than this?
Yeah, I'm not sure actually. I can't remember off the top of my head.
So the point is that much of the cycle comes from Doppler magnification, and it is quite large and low redshift, not high redshift.
Yeah, yeah.
We have a lot of data at low redshift, have more than
In principle, so when you show the signal to noise, in principle.
So this is for the bispectrum. Yeah,
Right.
yeah.
But one could tailor a survey that is smaller than Euclid on a patch of the sky and do a really good measurement together.
Possibly, yeah. Yeah, I mean, it's very sensitive to your largest wave number, Kmax, like everything else. We were quite conservative in modeling that. So the nonlinear scales would need to be added, can be added in, but need more careful modeling than we were able to do. So we did a fairly sort of crude Kmax of 0.1, something like that.
very good.
Okay.
We have no other questions. We're right on time. It's great. So let's thank our speaker again.
Okay.